Hello everyone. So, welcome to lecture 44. So, we were looking at Onsagers linear response theory to which we said is going to give us a generalized framework to describe the dissipative properties. So we just built up a bit of this, saying that okay, so I have a force and I have a flux, and the forces are related to fluxes. Flux is related to all sorts of forces, and it relates through these what are called Onsager coefficients, right. So the linear Onsager coefficients. Okay. So we were there and we ended by looking at the flux of a charged particle, some sort of charged particle in a system, which has a gradient of temperature, which has a gradient of stress, which has some stress, and which also has a gradient of or chemical potential, a gradient of these charged particles that can just come by applying an electric field, right. So, electric field will create separation in charged particles, and that is nothing but the chemical potential of these charged particles, right. So, this is one and the same. We said whether I look at it as gradient of chemical potential or just electrical potential, it is one and the same. So these two will be related as del mu q, or gradient of mu q equal to q times gradient of phi. Okay. So then we said all these coefficients are my Onsager's coefficients. Okay. So, let us start with a much simpler example today, and then actually go back to that problem that we were looking at. Okay. So, now in my material, right. So, I have atoms, this is my material, I have atoms, right, but when I apply some sort of an electric field, I have electrons that move, right. So, I have flux of electrons, right. I can also have flux of atoms, some sort of atoms, right. So, if I have some concentration gradient, right. So, if I just have atoms, right. So, if I have more concentration of atoms here, so so C1 here and C2 here, I have a concentration gradient and I have flux of atoms, right. So, I can in general I can have flux of atoms, correct, if there is a concentration gradient. That is a direct way of creating flux of atoms, right. So, if there is so here I am just going to say J A equal to minus L A times del mu A, right. So, this is flux of atom A, right. So, is dependent on the chemical potential gradient of that atom between this end and this end, right. So if it is supposed to move that distance, right, times some sort of an Onsager coefficient, right. And you can see that this is nothing but this will be related to di del Ci, right. So the mu's are related to C's, and so this will be related to this sort of an equation where di is nothing but the diffusion coefficient, right. Actually mu will be kT ln some sort of a concentration term. So you can relate these two things. So essentially there will be some term that comes out here, and you have del Ci will be related to delta of mu A. Okay. So it's going to be some sort of a simple conversion, no problem, we can do that. Okay. So a concentration gradient creates some diffusion, right. So Onsager's equation is actually saying exactly that, right. So this is the direct case, right. So if I have a concentration gradient, I am going to have diffusion of atoms. Okay. So here in this problem I have both electrons and atoms, both of them can diffuse, right. So now let me look at how the electrons are going to move around. So there is going to be a flux of electrons, and this flux of electrons is a direct electron so direct coupling of electrons, right. So electron flux can be created if I have a gradient of electron potential, chemical potential, right. And it can also be created since if I have a gradient of atomic the chemical potential of atoms, right. So if atoms are not in the same concentration throughout the wire, atom A has a different concentration here and a different so there is an inhomogeneity in atom concentration. then I can have a flux of electrons, right. So, flux of electrons is not just related to the chemical potential gradient of electrons, but also chemical potential gradient of atoms, right. Now, okay, I make materials which are more or less homogeneous. I made a homogeneous material where concentration of atom A Ca is equal to C, and here also Ca equal to C. So, if I plot Ca versus x, x is this dimension, right, then I have a flat line, right. I do not have any gradient of concentrations, right, all the concentration is uniform. Okay. So, then if concentration is uniform, then Je is just minus Lee del mu E. Okay. So, gradient of mu E. Now, what is this? This is just a simple so I said the gradient of chemical potential of electrons is nothing but minus E, which is the charge, times the del gradient of phi, which is the voltage that I am applying, right. So, or electric field that I am applying. Okay. So, Je is then equal to E times Lee times del phi. So, E times Lee or gradient of phi, this is my conductivity, right. So, sigma, right. So, this is nothing but Ohm's law, J equal to sigma E, right. So, this is E, this is J, this is sigma. So, so this is my Ohm's law, right. So, yeah, so this is flux of electrons, actually minus of this will be sigma, because flux of electrons and flux of current will have opposite directions, right. So, if I actually put it as flux of current as sigma times del phi, then Je equal to minus J, right. So, which is equal to Lee del phi. So, E times Lee will be equal to minus of sigma, right. So, this is the relation between Onsagers direct coefficient and the Ohm's law, right. So, and the sigma that comes out of Ohm's law, this is just conductivity. Okay. But okay, so if there is already Ohm's law, why do we need this Onsagers theory, right. Now, I said delta mu or gradient of mu of atoms is equal to 0, right. So, I have a homogeneous concentration of atoms throughout my material, right. So, this is all homogeneous, C versus X, this is quite homogeneous. Okay. So, if I look at atom flux, however, now this atom flux has so it should be equal to minus L atom electron, right. So, that is the cross coupling coefficient, Onsagers cross coupling coefficient, times gradient of mu electron minus okay. So, let us start with atoms, mu atoms minus La electron gradient of mu electron. Aha, now I am speaking. Okay, delta mu or gradient of mu A is 0, that is fine. So, I do not have any concentration gradient, but does that mean can I still not move atoms? That is not true, right. So, Ja now is equal to another Onsagers coefficient, this is a cross coupling coefficient, times the voltage, right. So, so this will just turn out to be E times Lae times del phi, and del phi is nothing but the electric field or the voltage that I am or the potential difference that I am applying in this entire wire, right. So, in this entire wire I connect it to a battery, right, and then I am actually looking at whether atoms can move in this wire, right. So, just by connecting it to a battery, there is all this is a homogeneous material, right. Just by sending in current or just by having some potential, right, can I create an atomic motion, right. So, in this material, right, indeed you can, right. So, I am sending in a current, the current that I am sending in so let us say I send in some current, right. So, I have a current source, not a voltage source, I have a current source. This is the material of interest, I have a current source. Okay. So, I am sending in some current Je, right. Now, Je is equal to minus LEE. Now, what is JA? Can I have a current of atoms? That is the question, right. So, that is minus LAE del mu E again, right. So, now del mu E is nothing but it is just minus E times del phi, or so gradient of phi, right. So, this is what we already know. Okay. So, I am sending in a flux of current, flux of electronic current, and I get atomic current, right. So, that is how much atomic current I get just depends on the ratio between these Onsagers coefficients. So, this is the cross coupling coefficient. So, this couples the electron flow with the atom flow, right. So, this is a cross coupled coefficient, or this is what is called electron wind force. It tells me just because of electron wind, right. So, there is some wind of electron. How much so how does this wind of electron transfer its momentum, right. So, this is a momentum transfer process. Momentum transfer from the electron wind to the lattice, right. So, that is nothing but electron wind force. Okay. Now, it is as if just by applying JE, right. So, electron wind, I have a force, right. So, that is actually transporting my atoms, right. So, this LAE describes how much that force is. LAE by LEE is actually equal to JA by JE, right. So, there is no minus here. Okay. So, I know what JE is. So, LEE sorry, JE is just so this is, so let us just not worry too much about J. E times, okay. So, fine, so E, there will be an E also here. Okay, anyway, that does not matter. So, the LAE by LEE is JA by JE. Okay. So, what I have is here my electron wind is transferring momentum to the lattice, and that is actually transporting atoms in the lattice, right. Sorry, let me rephrase it. It is transferring it is transferring momentum to the atoms in the lattice, right. So, these atoms are all fixed to their positions, right. So, and they are just vibrating, but this is transferring its momentum and it is making them move, right. So, this JE is making the atoms move through what is called an electron wind force, and that phenomena, I do not know if you have recognized it by now. This is nothing but the so called electromigration, right. I have an electric current, and this electric current is actually transporting atoms in my material, right. So, Onsagers actually theory explains you electromigration. Simple Ohm's law does not explain you electromigration, nothing else explains you electromigration, but this Onsagers theory couples the force on electrons, right, which lets them move, doubles up as also force on atoms, and then it makes them also move from their equilibrium positions, right. So, there is going to be an electromigration, which is a problem that you want to avoid in most cases, right. So, in all these interconnects that are there in your semiconducting chips, right. So, you have copper interconnects mostly, right, and sometimes so if you are passing too much current through these copper interconnects, they can sort of electromigrate, and then these wires can break, and so the shapes can change, etc., right. So, it is not a very good problem to have at hand, right? You want to solve the electromigration, right. So, you want to be able to, your design constraint then will be to be able to reduce the LAE, reduce the coupling between electron wind and the lattice, right. So, even though the force is large, the atom should not respond, right. So, you want to design your material in such a way. Okay. Now, let me show you some of the videos of this electromigration that happen. So here this is just from my work. So I did this work, so there are no copyright issues here. So in fact I have cited the paper also. Now here's a nanowire. This is a nanowire of what is called germanium telluride, right. And then I am sending in current, I believe in a certain direction, I believe in this direction I am sending in current. This is just electronic current or hole current, but it is charge current in some sense. Okay. Now you will start seeing once I start increasing the amount of current, the value of current is here, this video is sped 40x, and this is acquired in what is called a transmission electron microscope, a TEM, right. So while I am sending in current, I am just imaging the nanowire to see what happens. So this is the nanowire, it looks dark, it is quite thick, okay. So but let us see what happens to this nanowire as I start increasing the current. Right. So that is, I was just shaking, so I was trying to see which region in the nanowire should I be observing. So that is nothing, that initial disturbance, and so if you are paying attention, there is something that seems to be moving, right. And as the video progresses, this is 640 microamps, right. So that is quite large current for these nanowires. So the electron wind force is quite large. In fact, you can see on the sides there is some motion, right, of atoms, and finally it just there is so much of motion of atoms, it is also getting heated up, and finally the thing just melts and escapes, right. So this is all done in a vacuum chamber. It is a good video to watch, right. So the whatever is inside has just melted and escaped, because it is also heating, Joule heating is also happening, but there is also a migration of so just because of current there is a migration of atoms, right. So there is an electromigration phenomenon that is happening here. So let us watch it again, probably from this portion onwards. So you can see that there is some flow of material from the sides, at least there you can see something quite clearly. So there it starts to flow and eventually it just melts, right. So part of it melts and escapes, and so the rest of it just flows on this side and that side. Okay. So this is electromigration in an exaggerated way. So this is not just I am also creating I am also heating the nanowire, right. So it is not just that I have an electron wind force that is moving the atoms, it is also heating the lattice, and still the atomic motion still becomes more pronounced in that fashion, right. But here the amount of current, and I am not going to melt the nanowire, right. So there are already all these features on this nanowire, right. So these are what are called domain boundaries or twin boundaries. Again, it is the same nanowire, germanium telluride nanowire, and now I do some other form of biasing. I am still putting in electric current, right, but I am putting it in sort of a pulsed fashion, right. And you can actually see that so there is some mass motion, right. So with current moving in this direction, you can see there is reorganization of all these things, there is some sort of a motion in general, right. So this is a very controlled form of atomic motion, if you will. Okay. So and something else happens, we do not worry too much about what happens there, but you can see all these defects sort of moving in an organized fashion in this direction, right. So along with the electric wind force, along with the carrier wind force, the defects are also moving, right. So these are examples of what is called electromigration. Here in this case, because of something that I do, this is more sort of controlled electromigration. Here in this case, it is sort of uncontrolled electromigration. It is the same wire, right, depending on how I apply the initial bias, right. So whether I send in large current continuously or whether I send in pulses of current, right. So I can control the electromigration, right. So that is essentially my design that I am doing, right. So this is uncontrolled electromigration, but in this there is also heat and increase in temperature, all the other things are happening. Okay. All right. So that is electromigration for you. Okay. So now let us get back to our favorite equation. where we are actually looking at several such coupled terms. So, I said I have charge transport, I also have heat transport, and I have something like strain transport, right, or in other words dislocation transport. Strain rates we said is nothing but dislocation transport. Okay. So, our charge flux, heat flux and strain flux or dislocations, right. So, in my problem, but when I say strain flux, so you know that you have to go into that regime where dislocation number is conserved, right. So, with that assumption I wrote J q is equal to minus L q q gradient of T minus L q q del phi, right, E del phi. So, it will be q del phi, right. So, actually del mu E, but that is the same as q del phi minus L q x gradient of strain potential stress potential, right. So, that is just the force, right. So, mechanical force, this is the electric field, this is the gradient in temperature. Okay. Okay. Now, what is this, right. So, we said J q goes as L q q times q, right. So, this is my this is related to q times L q q will be related to the sigma, right. So, this is my conductivity, right. Okay. So, conductivity is easy to understand. What is this? This is by so you will quite so by having a gradient of the L q capital Q says by having a gradient of temperature or by having a thermal force, I am creating an electric current. Okay. So, this effect is what is called thermoelectric effect. Okay. And we will see that this coefficient is something similar to what is called Seebeck coefficient. I mean, it is something more than this, but so we will have what are called Seebeck coefficients in thermoelectric effect. So, this is related to Seebeck coefficient. This is related to LQQ is related to conductivity. Now, what is this? So, the third term minus so let me change the color minus LQ capital X gradient of phi x, let me write this as x. Okay. So, that means that I apply mechanical force and send in more current, right. So, and change the current, change the electrical current that I am sending in. So, in other words, if I have just a nice small resistor, right, I apply voltage, I measure current. Initially it is a linear resistor, right. So, it is going to be like this. This is at x equal to 0, which means I did not apply any stress. Okay. Now, later I apply some stress, right. So, with x equal to non-zero, I have a different curve, right. So, here I am sending in more current at the same voltage. Okay. So, in other words, I change the effective resistance, right. So, dV by di or V by I gives me the resistance, right. So, effective resistance or conductance by applying stress, right. So, I changed so by applying stress I am generating more resistive current or so this property so stress is piezo, right. So, and I am changing the resistance of the material. So, this property is called piezo resistance, right, which means I apply stress and I change the resistance of the material, right. And my LQX, sorry, L small qx, this is what gives me the piezo resistance property. Right. So, this property here, this is related to piezo resistance. Okay, this is only in JQ. What about so I can do the heat transfer problem, but let me look at the strain flux, right. So, now what is strain flux? So, I am going to write it as J strain for lack of J x. Okay. Now, that is equal to minus L x q del phi. Phi is just change in electric field or electric potential, right. So, there should be an E that comes out, sorry, there should be a Q that comes out, okay, minus L S Q gradient of T by T minus L S, sorry, x x gradient of phi s. Okay. Now, what am I saying? If I just take a direct, so if I just look at the mechanical problem, I am just saying J x is equal to minus L x x del phi s, right. So, or in other words, strain rate is proportional to, right. So, there is some viscosity term here, it is proportional to the stress that I am applying, okay, or force that I am applying. Okay. Now, this is very similar to the in a spring mass, F, the friction force F equal to minus C x dot, right. So, this is very similar to that, right. So, my Lxx tells me something about the friction force, friction coefficient or inverse of it. Okay. Or so what is this mechanism where, so this is like a damped spring mass system. This is analogous to a damped spring mass system. Okay. In materials, right, so by applying stress or by applying force, the material is just expanding, right. So, with some friction coefficient, right. So, it is just there is a strain rate by applying force, and this phenomena is called creep. So, what Lxx determines to me is creep. So, if Lxx is large, so even with small force the creep is going to be large, or the extension of the solid, right. So, the flow of the solid, right, the strain rate is going to be large. If Lxx is small, the strain is going to be small. Okay. Then so I can this is nothing but I am generating strain rate, not just strain, by gradient in temperature, right. So, this is the so called piezothermal effect. Sorry. So, piezo means stress. So, I am not applying stress here, but yeah. So, I do not know what the name of this is, right. So, you can make up a name. Then I am just by applying potential, right, or electric field, I am creating some sort of a strain strain gradient in the material, right. So, all these are something that one needs to avoid in regular devices and regular materials, right. So, but just by applying electric field, I cannot just be flowing the material, right. So, that's a bad thing to do. Okay. So, this is also some form of a creep. This is electric creep, this is thermal creep, right. So, and so on and so forth. Okay. So, now you see how so I put together several laws, right. So, there is Fick's first law of diffusion, there is Ohm's law, there is Fourier's law of heat conduction, there is piezo resistivity, there is creep, right. There is, what are the other things that we just saw related to sigma? Okay, so Seebeck effect or thermoelectric effects. There is electromigration, right. All these things come from one single framework. They all come from Onsagers framework. Okay. That is it. I do not have to study about 20 different laws. Rather, I can just understand Onsagers framework and say that, okay, Fick's law is just a specific case of Onsagers framework, right. Ohm's law is another specific case. Thermoelectric effects are not explained. I know I do not need a separate theory for that. I can just explain it through Onsagers framework, right. Electromigration, I do not need another special theory for that. I will just explain it through Onsagers framework, right. So, Onsagers theory is the BAP, right. So, I do not know how many of you know Hindi here, but it's the father of all the so I mean in Hindi it makes it gives you the effect that it deserves, right. So, not so much in English, but it's what is called the BAP of all the dissipative properties, right. So, it explains all sorts of dissipative properties, right. So, all the dissipation theories. Okay. So, as a result, so Lars Onsager has a Nobel Prize for giving this sort of a generalized framework. It actually goes much more, all right, but I am not going to go much deeper into Onsagers framework, right. So, I have just introduced you to what Onsagers theory is. Okay. Now, all right, so there is more, right. So, okay. Let us talk about so let us then generalize it, right. So, I have forces F1, F2, F3, right, and I have flux of just F1, let us say L11, F1, L12, F2, L13, F3, and this F1, F2, F3 are some sort of a gradient of some potential. This can be chemical potential, this can be electrical potential, this can be mechanical potential, okay, or chemical potential of species 1, chemical potential of species 2, chemical potential of species 3. If I have multiple species in my material and if I am trying to look at diffusion of all the species 1, species 2, species 3, hydrogen, helium and some argon, right. So, if I am looking at diffusion of all the 3 materials, then every individual material, their chemical potential gradient gives you the force, the chemical force. Okay. Then, so I can look at J2, which is the flux of 2, that is L12 L21 F1 plus L22 F2 plus L23 F3. J3 will be L31 F1 plus L32 F2 plus L33 F3. Okay. Now, imagine that my delta T equal to 0, I do not have any gradient of temperature, I do not have any gradient of stress, which is mechanical forces are 0, I do not have any gradient of chemical potentials of any species, right, or ions, that is equal to 0. All I have is electrical potentials, right. So, then I can write J1, which is so I have a wire where I am sending in current, right. Okay, so this is J1, this will be J2, this will be J3. Okay, so in different directions I have different fluxes of current. Okay, so J1 will be L11 F1, where F1 is nothing but so it is my electrical potential, the gradient of electrical potential in direction 1, right. So if I apply a battery like this, the electric field in direction 1, right. So that is Q times E1, right, plus QL 12 times E2 plus QL13 times E3. Okay. Okay, so in some sense this actually looks like sigma 11 E1 plus sigma 12 E2 plus sigma 13 E3, right. So the different tensors, right. Similarly, J2, the different elements of the sigma tensor. J2 equal to again QL 21 E1 plus QL22 E2 plus QL23 E3, and J3 equal to QL31 E1 plus QL, I mean I do not even need to write Q ideally, but it is fine. So, 32 E2 plus QL 33 E3, right. So, if that is the case, then so I mean, so the I am not going to prove it, I am just going to state it, right. So, now Onsagers these coefficients, right. So, I have the L11, L12, L13, L21, L22, L23, L31, L32, L33, right. So, I can write it as that sort of a so I can just combine the coefficients. I am not going to call it a matrix, but it is going to be some sort of if I am just talking about one property, the sigma, then this is a sigma tensor, right. Now, so there are certain rules for Onsagers coefficients, and one of the rules is what is called reciprocity. I mean, okay, so let us start with the first rule. So, I am just going to mention it here. Rule 1, Lij, any coefficient, is independent of F1, F2, F3, whatever, right. So, this L itself is not dependent. So, in some sense I am saying that sigma is not dependent on the electric field that I am applying, right. So, this means so this is a consequence of linearity, right. So, the slope, right. So, this is let us say E versus J, right. The slope is independent of E, okay. So, or if I just plot the slope, which is sigma as a function of E, that is just going to be a constant, right. So, irrespective of what E it is, the slope is constant. That is because so I am just looking at Onsagers linear response theory, right. So, this is a consequence of linearity, right. Okay. Now, let us not break linearity for just the sake of Onsagers response, right. So, in case of other equilibrium properties, we broke the linearity, we went to second harmonic generation, we went to all these higher order properties, right. So, here let us not break the linearity. Rule 2, so there is something called reciprocity, okay. This is Onsagers genius. Again, I am not going to prove it to you, but all the Onsagers coefficient, it does not matter which coefficient it is, have this property that Lij equal to Lji, okay, which means so here if I say so this is exactly why I have been considering all these sigma matrices sigma tensors etc. as symmetric tensors, sigma 1 2 equal to sigma 2 1, right. So, what is sigma 1 2? Sigma 1 2 tells me that if I have an electric field in direction 2, what is the current in direction 1, right. So, that is sigma 1 2, right. Turns out that if I have current in direction 2, that will be related to electric field in direction 1 exactly with the same coefficient. These two are the same, okay. Since I have this also, there should be sigma 2 2 E2, this will be sigma 1 1 E1, this will be sigma 2 2 E2, right. So, these are the direct so I have E1 and J1 in the same direction as E1. So, this is J1, this is E1. Here this component is E2 and J2 in the same direction as E2, that is okay, right. However, what I am saying is J1, which is in the component in the which is given by E2, is exactly the same as J2 that is given by E1, right. So, so these are about the cross components, right. So, if I just apply E2, I will have a J1. So, this is E2, I will have a J1, right. But if I apply the same magnitude of electric field in the one direction, that is okay. So, let's put it as red, right. I am just going to apply the red electric field here, E1, which is in magnitude the same as E2, then I rest assured what I will get is a J2 which is in magnitude equal to J1, okay. So, whether I do this problem or whether I do this problem, it is one and the same. So, that is Onsagers reciprocity. So far so good, it works in most cases, right. So, so recently people have been saying that you can break Onsagers reciprocity and go towards non reciprocal systems. They also exist, especially thoroughly nonlinear systems can break Onsagers reciprocity, but if a property is dissipative in nature, right, Onsagers reciprocity should hold. Okay. Now, Onsagers theory also so you can extend it to more sort of non-dissipative properties also. Okay. So, let us not go there, that is beyond the scope of this course. Okay. If someone is interested, you can email me and I will send you papers, and you can actually see how much more breadth is there for these Onsagers theories, but let's not go there, right. So, if a property is dissipative, Onsagers reciprocity relations are valid. Okay. So, let us put it that way. Okay. And the way I did all the derivations is by assuming that all my properties are dissipative, right. So, I have a T s dot. If T s dot exists, if I am generating entropy, right, over time, then there is always Onsagers reciprocity. Now, the exceptions come when I generate entropy and take it back. So, when I am oscillating, right. So, entropy is generated, and in the next time instance, so entropy sort of does not just keep going up, but it is generated, destroyed, generated, destroyed, and so on and so forth, right. So, this is where exceptions come, and those properties turn out to be non-dissipative. Again, they are not thermodynamic properties, they are also non-equilibrium properties, but non-dissipative, and Onsagers reciprocity is not valid, right. So, but this is the exception, and this course does not deal with such cases, right. So, it does not look into exceptions. Okay. So, with that so let us end this class here, right. So, in the next class we will look at a couple more examples of the thermoelectric effect that comes because of Onsagers theory, and we will try to calculate certain coefficients, such as what is Seebeck coefficient, what is the Peltier effect, how can I refrigerate things, right. So, so I have what are called Peltier coolers, right. So, that just works on the principle of thermoelectricity, and thermoelectricity comes from Onsagers framework, right. So, let us look at these two examples in the next class, but until then I will take leave. Thank you very much.